Welcome to GR Hub Mathematics and Statistics lessons. Today we are going to be talking about circle geometry part 3, where we will be proving the theorems we earlier stated in circle geometry part 2 of our videos. Okay, so you watch our video on circle geometry part 2. We stated that we will be proving 8 theorems in circle geometry. That is not to say that there are 8 theorems altogether in the field of circle geometry. Please, there are more than 8 theorems in circle geometry as an area of mathematics. So we stated we will be proving 8 theorems, and we are going to start right away with proving the very first theorem. But before we do that, let me say that there is a system for proving theorems in circle geometry. So you start with stating what is given, and to state what is given simply implies taking out those particular items in the theorem that were provided by the theorem. In stating next follows what you want to prove. So after stating what is given, you have to go straight into stating what you want to prove. And what you want to prove is also contained in the theorem. So you have to pay very close attention to the theorem. Then comes construction. So if you try to picture what the theorem states diagrammatically, you would notice that the diagram you would get from the theorem directly is somehow deficient. So to make embellishments on that particular diagram you've gotten straight from the theorem is simply a construction. The construction makes you see clearly what is not clear from the theorem when pictured diagrammatically. Then comes the last item. When you do the construction, certain things that were not clear becomes very obvious, and from there you can now make deductions or provide evidence with which the theorem can be shown to be true or false. So let's start straight away with theorem 1. What did theorem 1 state? Earlier on in our class on circle geometry part 2, we stated that theorem 1 was all about a perpendicular line drawn from the center of a circle to a chord which is not a diameter. Now, we stated in that theorem that when a perpendicular line is drawn from the center of a circle to a chord which is not a diameter, it will bisect the chord. I repeat, a perpendicular line drawn from the center of a circle to a chord which is not a diameter will do something to that chord. It will bisect the chord. It means it will divide the chord into 2 equal halves. Okay? So, now I'm going to put this diagram to you. To prove this theorem, here's my diagram, straight from the theorem. A perpendicular line is drawn from the center of a circle to a chord. So, in the theorem, we are given a circle AB. Now take note, I named my circle AB simply because I needed 2 points according to the theorem to make that chord from which the perpendicular line from the center will be drawn to. So I chose AB. You could have chosen CD, you could have chosen any letter at all, but I chose A and B because I need them to draw my chord. And in that same theorem, something was mentioned about the center of the circle. So the chord was drawn from the center of the circle. So nobody needs to tell you that contained in the theorem is that provision for where the chord was the perpendicular line was drawn from. So that being said, go straight to what you want to prove. What do we want to prove? If the perpendicular line drawn from the center of the circle to the chord which is not a diameter bisects the chord, then it implies that the chord, if the chord is actually AB in length and the perpendicular bisector meets that chord at a point we call C, then it implies that we want to show that AC is equal to BC. The length of AC is equal to BC. So that gives us this, what we want to prove. That's how we came about this. Now, going to the construction. By the theorem, what we were given was just a circle, this circle with center O and the chord AB. Now, this straight line drawn from O to B was a construction done by you, the student, in this case by me, and this straight line O to A was also drawn by me. It is just a construction. What does the construction do? It shows us clearly that we can actually develop the diagram, the initial diagram, into a triangle. There are 3 triangles there: triangle AOB, triangle AOC, which is a right angle triangle, and triangle BOC, which is also another right angle triangle. Now, the proof to this theorem is made easy when you understand congruence of shapes. The proof of this theorem relies on the congruence of shapes. So congruence is a means of comparing two diagrams or two plane shapes for equality, okay, or for equivalence. So now let's look at it. So what we did as our construction was to join O to A, center O to A, and to also join center O to B. Now we drew a perpendicular line also. We constructed a perpendicular line from O that met AB at C. So that was the construction. Those were the constructions done. Now that being said, it now brings us to proof. What can you see from the diagram? Having done that embellishment by means of construction, you would come to realize that to the two triangles we are comparing for congruence, AOC and BOC, the line OC is common. Now, one thing I want to state here to any student listening to me right now is that in circle theorems, when you state a particular evidence or you state a particular item in your proof, you must provide a reason for it. So the reasons are always put in bracket beside the statement you've made. So when I say line OC is common. So that is evidence number one. Now, the next evidence is that AO is equal to BO. And why is that so? It is because AO happens to be a radius and OB is also BO is also a radius. So AO is equal to BO, the length of AO is equal to the length of BO, and the reason is because they are radii. Now, the third evidence is coming straight from what was given to us by the theorem. The theorem told us what that perpendicular line would do to the chord. And because it is perpendicular, it means it forms an angle 90 degrees when it meets the chord at C. Now, that means that angle ACO, this angle here, this angle I'm pointing at is 90 degrees according to the theorem. And angle BCO is also equal to 90 degrees according to the theorem. So that's the reason why we are writing given. It was given to you by the theorem. Now, if you come over to congruence, the congruence relationship between the two right angles, you will notice that the congruence relationship is such that two sides and an angle are common or are the same for both triangles, and as a result of that, it implies that the third side which is left out will be equal to the third side which is left out for the other shape. So by congruence, SSA side angle, AC is equal to BC, and that proves that theorem. Go over what I've just said and you will understand better. Thank you very much. Now, for the proof of Theorem 2, Theorem 2 states that a straight line drawn from the center of a circle to a chord which is not the diameter and which bisects the chord is perpendicular to the chord. It is different from Theorem 1 that states that a perpendicular line drawn from the center of a circle to a chord which is not the diameter will bisect the chord. It is different. Okay, so we want to prove Theorem 2. Theorem 2 also happens to be a corollary to Theorem 1, implying that Theorem 2 is a consequence of Theorem 1. Now, if we are given circle AB with center O, of course we are given circle AB with center O because we need 2 points on the circumference of this circle with a known center in order to prove the theorem. Okay, then we want to prove that angle ACO is equal to angle BCO and both of them are equal to 90 degrees. Of course, these what I've just stated is with reference to this diagram. We want to show that angle ACO, this angle here, is equal to angle BCO, this angle here on this other side, and both of them are 90 degrees, provided what is stated in the theorem is true. So our construction requires that we join O to A and O to B. So we are going to join O to A and O to B. And our construction also requires that we draw a straight line from O to C to meet AB at C, such that AC is equal to BC. Of course, you must take note of the fact that in that theorem, it is stated that the straight line drawn from the center of the circle to this chord and which bisects the chord is perpendicular to the chord. So we were told the straight line drawn from the center of the circle to the chord already bisects the chord. So that's where that is coming from. Now, we can now start checking out for evidence. Take note, OC is common to both triangles. Triangles ACO and triangle BCO, or triangle AOC and triangle BOC. So to both triangles, take note, triangle AOC and triangle BOC, this line OC is common. So that is evidence number one. Evidence number two is that the length of AO is equal to the length of BO. And why is that so? The length of AO is equal to the length of BO. That is simply because they are radii. Then evidence number 3 is that AC, the length of AC is equal to the length of BC. How do we know that? It is given by the theorem. The theorem told us that the straight line drawn to AB is actually a bisector. So now by congruence SSS side of the triangles AOC and BOC, by congruence of this triangle to this triangle, you will notice that this angle here certainly must be equal to this angle, since the 3 sides of both angles are respectively equal. So now that we can deduce from that congruence that ACO is equal to BCO, okay? But in particular, notice that ACO is equal to BCO, but when both of them are added, according to the sum of angles on a straight line, they give us 180 degrees. Remember, sum of angles on a straight line equals 180 degrees. So if you replace BCO with ACO, because both of them are actually equal, it gives us ACO plus ACO, and ACO plus ACO adds to give you 2ACO. Both of them will now add to give us 180 degrees. So 2 angle ACO is equal to 180 degrees, implying that angle ACO must be equal to 180 divided by 2. And 180 degree divided by 2 will give you 90 degrees, implying that angle ACO is equal to 90 degrees. And since angle ACO is equal to angle BCO, then ACO is equal to BCO and is equal to 90 degrees. So let's move over to Theorem 3. Now, what does Theorem 3 demand? Theorem 3 stated that the angle at center is twice the angle at circumference. The angle which an arc of a circle subtends at center is equal to twice the angle it subtends at the remaining part of the circumference. Now, in this particular theorem, 3 points on the circle are needed with center O to prove the theorem. So that brings me to circle ABC. Why is it circle ABC? It's because in that theorem, 3 points are needed on the circumference to prove the theorem. What will 2 of those points do? 2 of those points will be joined to the center to make the angle at center, and the 2 points will in turn be joined to the remaining point on the circumference to make the angle at the circumference. So that's the reason why what is given is circle ABC with center O. Now, what do we want to prove? If the angle at center according to our diagram is angle AOC, then it means we want to show that angle AOC, the angle formed at center, is equal to 2 times the angle at circumference, being angle ABC. So 2 times angle ABC is equal to angle AOC. That's what we want to prove. So what we need to do as construction is to join A to O and C to O. We will also join A to B and C to B. So those are the construction we will do first of all. Those are the constructions we will do first of all. Then the next construction to do after joining A to O and C to O, and also A to B and C to B, the next construction to be done will be to draw a straight line from B through O produced to D. To produce a line simply means to extend the line beyond its boundary. So from B to O is the line we've drawn, and that line BO or OB is produced to D. Okay, so that's the construction we have done. Why did we do that construction? You will see shortly. So the construction brings about this figure, and from this figure you can actually see that there's a triangle ABO and another triangle CBO. Those triangles together form the shape, okay? But if you take each of these triangles one after the other, let's start with triangle AOB. Rather, let's start with triangle AOB. Now, from triangle AOB, notice from triangle AOB that the exterior angle AOD is equal to the sum of the opposite interior angles. Now, the exterior angle of one side of a triangle is equal to the sum of the opposite interior angles. Now, it means that this exterior angle here, I'm going to call exterior angle AOD. This angle here, exterior angle AOD, is equal to the sum of the opposite interior angles, angles OAB, this angle, and angle OBA, this angle. So the exterior angle here is equal to the sum of the opposite interior angles, these two angles added together. Now, similarly, the exterior angle over here is equal to the sum of the opposite interior angles here, as we shall see. So coming over here, you would notice that exterior angle AOD is equal to angle OAB plus angle OBA, and that's the reason, exterior angle of triangle. Okay, now, but you must take note of one thing, that the base angles of an isosceles triangle are equal. Now let me bring you back to the diagram. This angle and this angle form the base angles of an isosceles triangle. What isosceles triangle is that? Triangle AOB. Triangle AOB is an isosceles triangle. Why is it an isosceles triangle? It is simply because AO is equal to BO. So an isosceles triangle is a triangle that has two adjacent sides equal. So AO is equal to BO, and that makes this triangle AOB an isosceles triangle. And by a particular theorem in geometry, this particular angle is equal to this angle because they are base angles of an isosceles triangle. So that means that, coming back here, angle OAB is equal to angle OBA, and that's the reason. Base angles of an isosceles triangle are equal. So if in place of OAB we replace if in place of OAB here we replace OAB, angle OAB, with angle OBA, it gives us this result, that exterior angle AOD is equal to angle OBA plus itself, OBA again. And that would imply that the exterior angle AOD is equal to 2 times angle OBA, okay, with reference to this angle, to this figure. Now, if we repeat the procedure we've just done using this triangle AOB, if we repeat the procedure we've just done using this triangle COB, now it will give us the same routine, it will give us the same procedure. That is, exterior angle COD will be equal to angle OCB plus angle BOBC. And I'm writing here same reason, meaning that the exterior angle of triangle is also equal to the sum of the opposite interior angles. That's why I'm writing same reason there. Okay, now similarly, just like in the previous case, this angle is also equal to this angle because both of them are base angles of an isosceles triangle, and that will mean that angle OCB is equal to angle OBC. That is, angle OCB, this angle here, is equal to angle OBC, this angle. So these angles added together will give this angle, and that brings us to what I'm calling equation 2. Okay, now that being said, bringing this together, that is adding equation 1 to equation 2. If you add equation 1 to equation 2, you would end up having that exterior angle AOD plus exterior angle COD is equal to 2 angle OBA plus 2 angle OBC. And that implies that angle AOC is equal to 2 when you factorize, in bracket, angle OBA plus angle OBC. And that gives you angle AOC equals 2 angle ABC. What, of course, is required by the proof. This. Okay? Now, I would want you to watch that video again. Just watch that part of the video again. And you can drop your comments in the box below. Okay? Now, let's go to proof of Theorem 4. Let's go to proof of Theorem 4. In Theorem 4, we want to show that angles in the same segment are equal. How do we show that angles in the same segment are equal? Okay, for this particular theorem, we are going to need 4 points on the circumference. 3 points will form one angle, 3 points will form another angle in the same segment, because we want to show that angles in the same segment are equal. So all we want to do is, given circle ABC with center O, we want to show that angle ABD, according to my figure, angle ABD is equal to angle ACD. That is, this angle is equal to this angle. That is our intention. We want to show that those angles are equal. Now, all we have to do as construction is to join A to B and D to B. We will join also A to C and D to C. Then lastly, we will join A to O and D to O. So those are the constructions we will do. And having done that, we will now come to making deductions from that diagram. So starting with the first one, Notice that according to theorem 3, we've just shown to be true, angle AOD, the angle at center, is 2 times this angle at circumference, angle AOB. So that is true, and that's what we have here. Angle AOD is equal to 2 angle ABD. Angle at center equals 2 times angle at circumference. Okay? Now, similarly, this angle at center, AOD, is equal to this angle at circumference, angle ACD. And that is also true. For the same reason, angle at center equals angle at 2 times angle at circumference. Now, if AOD and if angle AOD is equal to 2 angle ABD, and the same angle AOD is equal to 2 times angle ACD, what it means is that 2 times angle ABD, in this case, must be equal to 2 times angle ACD. Now, if that is true, then dividing both sides by 2 reduces the result to angle ABD equals angle ACD, and that shows our theorem to be true. Now, let's move over to theorem 5. Let's go to theorem 5. What did theorem 5 state? Theorem 5 stated that the angle in a semicircle is a right angle, meaning that the angle in a semicircle is 90 degrees. So all we have to do, remember from our first lesson on circle geometry, that is circle geometry 1, we mentioned something about the diameter, that the diameter is twice the length of a radius. Okay, so we also stated that a chord, when it passes through the center of a circle, gives a diameter. So in this case, the theorem requires that we are given circle ABC, and that is with center O. That's with center O. So we are given circle ABC with center O, and we want to show that the angle in this angle here in the semicircle is a right angle. Okay, that is, this angle is 90 degrees. That's what we want to show. That means angle ABC is equal to 90 degrees. So what construction are we going to do? We are only going to join A to B and C to B. We are going to do that construction. Once we join that, we now have, take note, 2 angles at center. Now in this case, since AC is a diameter, that is, in particular, it is a straight line, it means this angle here, I'm going to call angle ACO star. This angle is an angle on a straight line, and angles on a straight line, an angle on a straight line is 180 degrees. Okay, now similarly, this angle below is angle AOC. Now take note, both angles are AOC. I'm only using the asterisk here to differentiate between the AOCs. The 2 angles are AOCs, but I'm using the asterisk here to differentiate the upper one from the lower one. Now the one we really want is the lower one. We want to show that this angle AOC is equal to 2 times this angle, first of all, before we prove what is required. So now angle AOC is equal to 2 angle ABC. Why is that so? Angle at center equals 2 times angle at circumference. Okay, now, but in particular, angle AOC is equal to 180 degrees. Why is that so? It is an angle on a straight line. This angle is an angle on a straight line. Angle AOC is equal to 180 degrees. So by implication, it means that 2 times angle ABC, 2 times angle ABC must be equal to 180 degrees. And that implies that angle ABC is equal to 90 degrees. So that proves theorem 5. So take note again, the theorem demands that we prove that the angle in a semicircle is 90 degrees. So go over that again and you will get it better what I've just explained. Okay, now let's go to theorem 6. Let's go to theorem 6. Now in theorem 6, what do we want to show? We want to show that the angle BCE is equal to the angle BAD with respect to this figure. But I want to bring to your notice that for us to prove theorem 6, we have to prove theorem 7 first. Now, I'm going to bring theorem 7 forward before proving theorem 6. Why is that so? We need theorem 7 in order to prove theorem 6. What does theorem 7 state? Theorem 7 states that opposite angles of a cyclic quadrilateral are supplementary, meaning that opposite angles of a cyclic quadrilateral add up to give 180 degrees. Remember, two angles are complementary if they add up to 90 degrees, but are supplementary if they add up to 180 degrees. So opposite angles of a cyclic quadrilateral are supplementary. In this case, this angle ABC, we want to show it is actually equal to, it adds up rather with ADC to give 180 degrees. So this is a cyclic quadrilateral. I want you to check up our notes, our lessons on circle geometry 2, where we discuss cyclic quadrilateral. So this angle here plus this angle gives 180 degrees. So our construction demands that we join A to O, center O, and C to center O, because we have already been given a cyclic quadrilateral A, B, C, D. Remember, we said a cyclic quadrilateral is a circumscribed quadrilateral. Okay, so that being said, let's go straight to the proof. What are we going to show here? Take note, again, I'm using the asterisk AOC and the normal AOC to represent the two angles formed at center. In this case, we can't tell whether both of them are 180 degrees. So what we are going to do is this. We know from earlier theorem that the angle at center here, this angle AOC, is 2 times ABC. Okay, that is this. We know that asterisk AOC, this angle here above, is equal to 2 times this angle below. And we know that this angle here, AOC, is 2 times this angle. So that's what we have here. And the reason is that angle at center is equal to 2 times angle at circumference. But again, when you add these two angles at center together, they give you 360 degrees. Why is that so? It is simply because the angle at a point gives 360 degrees. I could as well write it here. Angle at center. Angle at center equals 360 degrees. Okay, so the angle at center equals 360 degrees. Therefore, when we add both, we get 360 degrees. But take note, angle AOC star is to angle ADC. Okay, we had already gotten that to be true. And angle AOC, normal angle AOC, is equal to 2 angle ABC. Again, what we derived here. And that would mean both of them now add up to give you 360 degrees, implying that if you factorize by bringing out 2 into bracket ADC plus angle ABC gives you 360 degrees. And that means dividing both sides by 2, you end up having the proof to be true. That is, angle ABC plus angle ADC is equal to 180 degrees. Now, having shown that to be true, that opposite angles of a cyclic quadrilateral are supplementary, let's now come back to Theorem 6. In Theorem 6, we want to show that the exterior angle of one side of a cyclic quadrilateral is equal to the opposite interior angle. So all I had to do in this particular theorem was to draw, to produce one side of the cyclic quadrilateral, the side DC. I had to produce the side DC to a point E. Okay, and the production simply means extending it beyond its boundary to E. Now, if you do that, it means we want to show that angle BCE is equal to angle BAD. That is this angle here, the exterior angle formed when one side is produced, is equal to the opposite interior angle. This angle here, this is the opposite interior angle. So what are we given in this theorem? We are given a cyclic quadrilateral. Remember, a cyclic quadrilateral is a circumscribed quadrilateral, or a quadrilateral that is bounded properly by a circle, ensuring that all points or vertices on the quadrilateral touches the circle and do not cross the circle. Okay, so the construction we are going to do here is just to produce DC, this line DC, to a point E. Now, once you get that construction done, you can now start searching for evidence. Now, evidence number 1 is that angle BCE, this angle here, angle BCE, when added to angle BCD, when added to this angle here, because DE is a straight line, when you add this angle BCE to this angle BCD, BCD. It gives you 180 degrees. And why is that so? Sum of angles on a straight line. Then if you add the same angle BCD, this angle here, if you add it to this angle by the theorem we've just shown, that is theorem 7, opposite angles of cyclic quadrilaterals are supplementary. If we add this angle to this angle, it will also give us 180 degrees. So if the sum of these two gives 180 degrees and the sum of these two also gives 180 degrees, what it implies is that both of them are equal to one another. We can actually equate them. So angle BCE plus angle BCD was 180 degrees, and this one, angle BCD plus angle BAD, was also 180 degrees, meaning that both of them are equal since they both add up to give 180 degrees. And that implies if you subtract what is common from both sides, that is angle BCD happens to be common to both sides. If you subtract it from both sides, you end up having what is left to be angle BCE equals angle BAD, and that completes the proof. Okay, now to prove theorem 8a, which states that the angle formed between a chord and a tangent at the point of contact equals the angle in the alternate segment, we are going to be needing a circle BEFD with center O and tangent ABC. Now the reason why we need those points I'm going to explain. The angle in this case, what we want to prove is that angle CBD is equal to angle BED. We want to show that this angle is equal to this angle, okay? This is the angle formed in the alternate segment, and this is the angle formed between the chord and the tangent at the point of contact B. Now, that is what we want to show. Now, you will notice that I have put a point F on the circumference of the circle, and in my construction, I'm going to be joining B to E and D to E. Now, the reason why we are joining B and D to E is to form the angle in the alternate segment, whereas the reason why we are joining B through center O to F and B and D to F is to form the angle in a semicircle. So we need this angle in a semicircle. This proof requires the knowledge of that theorem that said angle in a semicircle is equal to 90 degrees, a right angle. So what we are doing here is to make that construction to bring out this, which enables us to get this, okay? So now let's go to the proof. For the proof of the theorem, you will notice the following. Let's start gathering what we can actually notice from the diagram. Notice that this angle here, CBD, the angle here, CBD, this angle CBD is when added to angle DFB, this angle CBD when added to angle DFB will give you, or DBF rather, when added to angle DBF gives you 90 degrees. Where is that coming from? It is coming from the property 1 we stated earlier on, that the angle formed between a diameter and the tangent at the point of contact gives you 90 degrees. That is, once a straight line is drawn through the center of a circle, through the point of contact of a tangent to that circle, the angle formed is 90 degrees. So that's where that is coming from, okay? So angle CBD plus angle DBF equals 90 degrees, courtesy that reason. Now, let us go to the next point I want to make here. Angle BDF is equal to 90 degrees. And why is that so? Angle in a semicircle is 90 degrees. So this angle here is 90 degrees. Now, coming back to this triangle, if you come to this triangle, the sum of angles in a triangle is equal to 180 degrees. So this angle added to this angle added to this angle in the triangle there will give us 180 degrees, and that's because sum of angles in a triangle equals 180 degrees. So this angle here, the angle here is angle BDF, and this angle here is angle DFB. This angle here is angle DBF. Okay, so when you add this angle to this angle and to this angle, it gives us 180 degrees. So now take note of one thing. If we replace BDF, which is 90 degrees, with the item with BDF in the equation, you end up having that DBF plus 90 degrees plus angle DFB equals 180 degrees. Now that reduces it to equation 2. When you subtract 90 from both sides, 90 degrees from both sides, it ends up giving you angle DBF plus angle DFB equals 90 degrees. And that brings us to the two equations, equation 1 and equation 2. Now, when you compare equation 1 with equation 2, it reduces to this, because both sides have their left hand side, both equations have their left hand sides amounting to 90 degrees. So it means their left hand sides are equal. So CBD plus angle DBF will be equal to angle DBF plus angle DFB. So they both are equal, okay? Now, if you subtract from both sides, what is common? Angle DBF is common to both sides. So when you subtract it from both sides, you end up having that angle CBD is equal to angle DFB. And that gives us equation 3. Now, take note of one thing. The essence of this proof was not to show, that it wasn't to show that this angle DBF was equal, DFB was equal to this angle. We wanted to show that this angle is equal to this angle. But what we've been able to show so far is that this angle is equal to this angle. But what is the link between this angle and this angle? It is the fact that both of them are angles in the same segment. So if we've been able to show so far that this angle is equal to this angle, then it means we've invariably shown that this angle is equal to this angle, since this and this are equal. They are equal because angles in the same segment are equal. And that brings us to the end of the proof using the approach, the first approach. So let's go to the second approach now. The second approach to the theorem requires that we use the idea of cyclic quadrilaterals. So again, BEDF with center O and tangent ABC are what we are given. Now, this time around, based on the diagram, we want to show that this angle here is equal to this angle. So when the angle is formed here, remember what we said in our earlier note or video on circle geometry. When the angle is formed over here, then the alternate segment becomes this part, meaning that this is an angle formed in the alternate segment. So now the logic to proving this particular theorem requires that we use the idea of a cyclic quadrilateral. And the idea of a cyclic quadrilateral can only come in if we join B and D to F and to E respectively. So why do we need the idea of a cyclic quadrilateral? We can actually see from a cyclic quadrilateral that this angle plus this angle will give us 180 degrees. Why? Opposite angles of a cyclic quadrilateral are supplementary. Now, again, if you look at this diagram, you would notice that the angle over here, this angle plus this angle is equal to 180 degrees. That is this. CBD plus angle BABD. CBD, this angle here, plus angle ABD, this angle over here, would add to give you 180 degrees. They will add up to give you 180 degrees. So angle on a straight line gives you that. Now take note, from what we've shown in theorem 8a, this angle here is equal to this angle. That is angle CBD is equal to angle BFD. Okay, and that's because angle on angle formed between chord and tangent at point of contact equals angle in the alternate segment. So when you compare equation 1 and equation 2, you end up having that their left hand sides are equal, since their right hand sides are both 180 degrees. Now what is common, if you bring this, what we have here, that angle CBD equals angle BFD, cos C alternate segments, angle in alternate segments, then it means replacing it in this equation gives us this. Now if you compare the two sides of this equation, you end up realizing that we can actually subtract angle CBD from both sides, and that reduces the equation to angle BED equals angle ABD, which is the same thing as angle ABD is equal to angle BED, as the theorem requires. Okay, and that brings us to the end of proving the theorems on circle geometry. Do like our videos, share our videos, and most importantly, subscribe to our YouTube channel. Thank you.